Thank you very much. So, good day everybody. My name is Petr and I'm from Cake Solutions. In this presentation, I'm going to talk about distributed stream processing. This area attracts quite a lot of attention these days, and I hope you will find it interesting. Fuck it. We do not have much time, so this talk is designed more like an overview than like a deep dive. I'd like to cover following. Firstly, a motivation. What are the reasons behind this increasing demand for real-time data processing and how to address it? Then I'm going to talk about stream processing in general and also about challenges we have to expect. After that, I'd like to talk about available frameworks, their similarities and differences, and also their typical use cases. Finally, we'll conclude with general guidelines and recommendations. I like to say this talk is based on my personal opinions, and I'm definitely biased in some way. Huge amounts of data has to be processed fast from a rapidly growing set of disparate data sources like trading, social networks, IoT, system monitoring, and so on. And this pushes limits of the traditional batch processing infrastructures, which are often simply not good enough. And stream processing might be a good way to go. We want to process incoming data on the fly, and we want to be able to react to events as they occur, as latency really matters here. As you suspect, distributed stream processing is continuous processing, aggregation, and analysis of unbounded data. It is a general computational model as MapReduce, but we expect our latencies in millis or in seconds. These systems are usually modeled as didactic acyclic graphs, DAGs, or DAGs. DAG is a graphical representation of chains of tasks, and we use it for description of a topology of streaming job. So as you can see in the picture, data flows through chains of processors from sources to sinks, which represent a streaming task. When choosing between different systems, there are a couple of points we should have in mind. So let's start with runtime and programming model. The programming model provided by a platform determines all of its features, and it should be sufficient to handle all possible use cases for our application. This is a really crucial topic, and I will come back to it very soon. The functional primitives exposed by a framework should be able to provide rich functionalities at individual message level, like map or filter, which are pretty easy to implement, even if you want to scale a lot. But it should also provide across messages functionality, like aggregations, or across streams operations, like joins, for example, which are much harder to scale. Then we have state management. Most of applications have stateful processing logic, which requires maintaining a state. And platform should allow us to maintain access and update this state information. For message delivery guarantees, we have a couple of classes like at most once, at least once, and exactly once. Another important thing to consider. Failures can and will happen at various levels, like network partitions, disk failures, or nodes going down, and so on. And our framework should be able to recover from all such failures and resume from its last successful state without harming the result. And then we have more performance-related requirements like latency, throughput, and scalability, which are obviously very important in streaming scenarios. We should also take care of maturity and adoption level. This information could give us a clue about potential support, available AI libraries, or even Stack Overflow answers, and so on. And also, last but not least, the ease of development and ease of operability. It's great when we have a super fancy system which covers all of our use cases, but if we cannot write a program for it, or if we cannot deploy it, we are done anyway. So let's talk about runtime and programming model, which is probably the most important trait of the system because it defines its expressiveness, possible operations, and future limitations. Therefore, it defines system capabilities and its use cases. There are two distinctive approaches how to implement streaming system. First one, the native streaming execution model. It means all incoming records, or events if you will, are processed as they arrive, one by one. The second approach is called micro-batching. Short batches are created from incoming records and go through the system. These batches are created according to a predefined time constant, typically every couple of seconds. Both approaches have inherent advantages and disadvantages. So let's start with native streaming. The great advantage of native streaming is its expressiveness. Because it takes the stream as it is not limited by any unnatural abstraction over it. Also, as records are processed immediately upon arrival, achievable latencies of these systems are always better than its micro-batching companions. Besides that, stateful operations are much easier to implement, and fault tolerance is much more expensive as it has to take care of every single record. Also, load balancing is kind of issue. For example, let's say we have a data partitioned by a key and we want to process it. If processing of some key for partition is more resource intensive for any reason, this partition quickly becomes the job's bottleneck. Splitting streams into micro batches inevitably reduces systems expressiveness. Some operations, especially state management or joins and split, are much harder to implement as system has to manipulate with whole batch. Moreover, the batch interval connects to things which should never be connected, an infrastructure property and a business logic. On the contrary, fault tolerance is much simpler as system just sends every batch to a worker node, and if something goes wrong, it can just use a different one. Lastly, it's good to remark we can build micro-batching system atop native streaming quite easily. Programming models can be classified as compositional and declarative. The compositional approach provides basic building blocks like sources or operators, and they must be tied together in order to create expected topology. New components can be usually defined by implementing some kind of interfaces. On the contrary, operators in declarative APIs are defined as higher order functions. It allows us to write functional code with all its fancy stuff, and the system creates and optimizes its topology itself. Also, declarative APIs usually provide more advanced operations like windowing or state management out of the box. I'm going to show you some code samples really soon. There is a number of diverse frameworks available, and it's literally impossible to cover all of them in just one session. So I have been forced to limit it somehow, and I decided to go for popular streaming solutions from Apache landscape. Therefore, I'm going to mention Apache Storm and its sibling Trident, and the streaming module of very popular Spark, obviously. After that, I'm going to talk about the streaming system behind LinkedIn named Samza, and also about somehow related Kafka streams. Finally, I'd like to mention two vibrant Apache projects, Apex and Flink. I believe this is a great selection because even though all of them are streaming systems, they do approach various challenges very differently. Unfortunately, I won't talk about proprietary systems like Google Millwheel or Amazon Kinesis, and we are also going to miss interesting but still limitedly adopted systems like, for example, Interview Pump. Apache Storm was originally created by Nathan Martz and his team at Backtype in 2010. Later it was acquired and open sourced by Twitter, and it became Apache top-level project in 2014. Without any doubts, Storm was the pioneer in large-scale stream processing, and it became de facto industrial standard. Storm is a native streaming system and provides very low-level API. Storm also uses Thread for topology definition, and it implements Storm multi-language protocol. This basically allows us to write our applications in large number of languages, which is pretty unique. Trident is a high-level micro-batching system built atop Storm. It simplifies topology building process and adds high-level operations like windowing, aggregations, or state management, which are not natively supported in Storm. In addition to Storm, Trident provides exactly once delivery, and Trident has Java Closure and Scala APIs. As we all know, Spark is a very popular batch processing framework these days, with a couple of built-in libraries like Spark SQL or mmlib, and of course Spark Streaming. Spark's runtime is built for batch processing, and therefore Spark Streaming, as it was added a little bit later, does micro-batch. Stream of input data is ingested by receivers, which create micro-batches, and these micro-batches are processed in a similar way as other Spark jobs. Spark Streaming provides high-level democratic API in Scala, Java, and Python. Samza was originally developed in LinkedIn as a proprietary streaming solution, and with Kafka, which is another great LinkedIn contribution to our community, it became a key part of their infrastructure. Samza builds heavily on Kafka's log-based philosophy, and both together integrates really well. Samza provides compositional API. Kafka Streams is a library which runs on top of Kafka. So you don't have to deploy any dedicated streaming cluster, as running Kafka is all you need. Kafka Streams provides similar functionality like Samza, but with nicer APIs. Apex is a Hadoop-focused streaming system backed by ex-Yahoo engineers. It provides both compositional and high-level API, and you can also use its visual tool to assemble applications, which is quite nice. Besides that, Apex comes with a rich library of operators named Malhar. Apex implements an interesting compromise between native streaming and micro-batching. And the last but not least, Flink. Flink is a pretty old project. It has its origin in 2008, but right now is getting quite a lot of attention. Flink is a native streaming system and provides high-level API. Flink also provides API for batch processing, like Spark. But there is a fundamental distinction between these two. Flink handles batch as a special case of streaming. Everything is a stream, and I think this is a definitely better abstraction, because this is how the word really looks like. And now let's take a look at code samples. Word count is something like hello world of data processing. So let's start with Storm, and please note the example was simplified significantly. First, let's take a look at its topology definition. As you can see, we have to define a spot, or if you want, a source. And then there is a bot, the processing component, which splits text into words. Then I have defined another bot for actual word count computation. Also, take a look at the magic numbers, 5, 8, and 12. These are the parallelism hints, and they define how many independent threads around cluster are used for execution of every single component. As you can see, all is very manual and low level. And this is how is the actual word count bot implemented. As long as Storm does not have inbuilt support for managed state, so I have defined a local state, which is obviously far from being ideal, but good as a sample. Apart from that, it's not very interesting. So Let's take a look at Trident. As I mentioned before, Trident is Storm's micro-batching extension, and Trident, apart from many other goodies, provides stage management, which is pretty useful when implementing word count. As you can see, I could use high-level operations like each and group by, so it is a little bit better. And also I was able to use Trident manage state for storing counts. And now it's time for a pretty decorative API provided by Apache Spark. Also keep in mind, on the contrary to the previous examples, which were really simplified, this is almost all code you need to write or to run this simple streaming word count. Every Spark streaming job requires streaming context, which is basically the entry point to the streaming functionality. Streaming context takes the configuration, which is, as you can see in our case, very limited. But more importantly, it defines its batch interval, which is set to 1 second. And now you can see the whole word count computation. Quite a difference, isn't it? That's the reason why Spark is sometimes called distributed Scala. As you can see, it's quite a standard function code, and Spark takes care of topology definition and its distributed execution. And now the last part of every Spark streaming job, starting the computation. Just keep in mind, one started job cannot be modified. And now let's take a look at Apache Samza, another representative of the compositional API. The topology is defined in Samza's property file, so you won't find it here, but for us it's important that each task has defined input and output channels, and communication goes through Kafka's topics. In our case, the whole topology is this word count task which does all the work. In Samza, components are defined by implementing particle interfaces. In this case, it's stream task, and I have just overridden the method process. Its parameter list contains all what's needed for connecting with the rest of the system. And the computation itself is just a simple plain Scala. Kafka Stream provides both compositional and declarative APIs. Unfortunately, it has just Java API, so the code itself is not that pretty. But if you look at the implementation, I think it's quite self-explanatory. Just a couple of function calls, and that's it. And now the last part of, let's take a look at Apex. In this example, I use is compositional API, and again, the snippet was simplified. First, we have to define jobs topology. I have to add components to DAG and connect them with streams. And here is the definition of one of our operators. This one splits incoming strings. The code itself is pretty clear, I guess. And the last one, Flink. As you can see, API is pretty similar to Spark streaming, but notice we are not setting any batch interval. Computation itself is pretty straightforward, just a couple of function calls, and Flink takes care of the rest. So that was a basic comparison of chosen systems, which took me most of my time. You may take a quick look at this summary of, from my opinion, their key traits. Now it's time to move on to the last part of this talk, framework recommendations. I have to say this part is quite opinion-based, but I was really trying to be fair. So give me a sec. The answer for a typical question, which one should I use or which one is the best, is always, it depends. So in general, always try to evaluate requirements of your application carefully and be sure you fully understand the consequences of choosing a particular framework. And try fully understand its internals, as improper use may have disastrous consequences. For programming model, I think most of you guys would prefer high-level API, and it makes sense. It's more elegant, more productive, and so on. But on the other hand, high-level APIs might hide a lot of details you have to understand once you're facing an issue. And I have seen a lot of problems with that. So I would recommend following. If you want to do a lot of data science, analysis, or if you want to play with REPL, I think the high-level API is a great way to go. But if you expect more data-intensive operations, like crunching terabytes of logs, or if you want to manage your DAG really precisely, I think that compositional API might definitely make sense. So think through what do you need and which approach suits you better. I would also recommend going for a framework with all delivery semantics available, as you usually don't want to limit yourself, especially if you are not sure what to expect. And as we all know, this is quite common in our industry. But of course, there are definitely use cases when at least once or at most once delivery guarantees are all we need. And also keep in mind, which might be a little bit surprising, a system supporting exactly once does not have to support weaker guarantees. This point might be tied together with the previous one a little bit. Most of streaming applications are stateful, so the state management of a particular framework should be really up on your evaluation list. Lastly, make sure your system is able to recover quickly. You can use Chaos Monkey or similar tool for testing, because fast recovery is crucial in stream processing. You have to have in mind that data or new records are still incoming. And now let's take a look at particular frameworks. Storm still might be a good fit for small and fast tasks. If you care mainly about latency, Storm might be a good way to go. But keep in mind, the photo runs or Trident state management hurts the performance a lot. An interesting option might be a potential update to Twitter's Heron, which is designed as Storm's replacement and should be better in every single way. And what is more important, it keeps the API. And the best thing is, Heron was open sourced quite recently. It is a little bit uncharted territory, but maybe worth to check it out. For Spark streaming, you should definitely at least try it if Spark is already part of your infrastructure. Because in this case, streaming comes basically for free. And you can also take an advantage of various Spark libraries. Apart from that, there's a bunch of helpful tools available, like REPL, Spark Notebook, structured streaming, and so on. Regarding ecosystem, Spark is a step ahead. But you should always keep in mind micro-batching limitations, which may really become a showstopper. And also, be sure latency is not critical for you. When thinking about adopting Samza, Kafka should be a cornerstone of your architecture. I know it's pluggable, but nearly everyone is, or maybe everyone is using Kafka, so I will stick with that. Also, Samza is shipped with powerful local storage, and it's great for managing large states. It can handle states of tens of gigabytes easily, which is quite nice. But keep in mind Samza's at least once delivery limitation. Kafka Streams provides similar functionality like Samza, but with nicer APIs, and it's operated by Kafka itself. So big win both for operations and developers. Kafka Streams is probably not the best option for machine learning or analytics, but if it can be used for common stream processing or simple task very easily. If you prefer a low-level / compositional approach and you are also Hadoop positive, I believe Apex might be a great choice for you. It gives you fine-grained access to DAG, so you can get really most of it. Therefore, its performance, especially achievable latencies, are truly excellent. And the great thing is, if you change your mind, you can always try its high-level API. Moreover, Apex allows dynamic DAG changes, which is quite a unique feature. Flink is conceptually a great streaming system which fits very most streaming use cases. And it often provides progressive functionality like advanced windowing or time handling, which may not be implemented by its competitors. So you should always consider Flink when you need a functionality which may be hard to implement in Spark or generally in any other micro-batching system. Apart from that, Flink also has an API for a common batch processing, which may be pretty useful. And the last thing I want to mention today is Dataflow and its open source initiative. Dataflow is a part of Google Cloud Platform, and Cloud Platform has all sorts of things in it. It has huge data storage, BigQuery, Cloud PubSub, some tools for data analysis, and so on, and also aforementioned Cloud Dataflow. It is Google's managed service for batch and stream processing with unified API. And it is built upon well-known Google technologies, such as MapReduce for batch processing, from Java for programming model definition, and Millwheel for stream processing. And all of them are really good. It's Google. You may be asking why I'm talking about that. As I said, I will be speaking about open source frameworks, and this is clearly Google's proprietary solution. But Google decided to open source Dataflow SDK recently, and guys behind Spark, Flink, and Apex have already implemented its runners. And it is very probable more engine or more runners will follow soon. Dataflow provides API in Java and in Python, implemented by Google itself. And also I have found a couple of Scala DSLs already. Besides that, Google and a number of partners submitted this as a new Apache proposal / Apache project named Apache Beam. I think Beam has a good chance to be the unifying API that gives us the nice way to write once and run everywhere. But it's important to say all of this is quite recent, and the implementation of some of the promised features might be missing. But definitely do something worth to check it out. So now it's time for questions. So are there any? But also I'll be somewhere around anyway, and always happy to discuss various stuff. So just find me. I'd like to also say that we are hiring, so if you want to join us, please follow the link.
Well, a quick question, just one, I guess.
Thank you. Is there any recommendation for get file from FTP and the file is incremental? So I have so many edit file and incremented file, but I can't get just one time.
Okay, this is, I think this is quite specific, so can we discuss it after the session, because I think I need more information. Sorry.
All right. That's going to be the last question. We're running out of time.
This is actually more of a statement than a question, but I've also been following Apache Beam, and besides all the things that you mentioned, I think they're also trying to create a library of patterns for a lot of the things that we all try to do.
Yeah,
and that excites me more than where they're at right now.
Yeah,
In case
I'm
you
about
agree.
that. It's like Beam is a really interesting project. I really support it. It would be great that if this will work as as decided.
All right, let's thank our speaker. Thank you.
Thank you very much.